one extreme, we have this very simplified red-coded neuron models. Other extreme, you have spec neuron models, where again you have to go to very detailed levels. You can have detailed biophysical models. We start asking the question: is there a middle ground, right? And then we look at this abstraction of fluid flow and fluid mechanics. So similarly, can we think of the activity of a pool of neurons, a neural ensemble, right, as a right middle ground, as a right uh, fundamental functional unit of brain, and then describe all brain dynamics in terms of such a pool of neurons. And in that case, the activity, especially if you take a do a low pass filter, you get a smooth signal called the local field potential. Right now, once we talk about brain dynamics, not in terms of spikes, but in terms of these local field potentials, you can talk in terms of frequency bands, all this delta, beta, alpha waves, and so on. So you can use a lot of concepts from signal processing, from electrical engineering. Right? And so is there a middle ground there? Is there a grand theory of brain function which can be expressed completely in terms of oscillations, and therefore in terms of oscillators? So there are several people who are talking on these lines, and we started approaching this problem, particularly using what are called something called Hopf oscillators. So I'll come to that in a minute. But we've already seen a few oscillator models. We haven't seen Wilson-Cohen. Wilson-Cohen is given by this, right? And it's a two-variable model, and very similar to some of the models that we have seen in Fujino-Gumo and all. And so this also produces limit cycle oscillations. We have seen Fujino-Gumo model, right, which has limit cycle oscillations. Then Maurice-Lécart has similar dynamics. Van der Pol we haven't seen, but it also has limit cycle oscillation. And it is similar system, two variables, quadratic nonlinearity, and it has limit cycle oscillations. Now, the advantage of these two variable models is that, as we know, we can do baseband analysis, you can draw null lines and find fixed points, and all that. So that's the advantage. We know what limit cycles are, all this we have already covered. And then here again, this, if you look at the difference between the harmonic oscillator and limit cycle oscillator, in case of harmonic oscillator, which is defined by this equation here, it is the oscillation amplitude depends on the initial condition, whereas in case of limit cycle, it doesn't depend on initial condition. No matter where you start, the initial condition, it always goes to a particular closed loop solution, right? Particular closed loop in the state space. So here we will take specifically Hopf oscillator, right, which also has limit cycle, but compared to the other models like Van der Pol and Fujino-Gumo, Maurice-Lécart, and all that, it has a mathematical advantage. It's mathematically very simple, right? So it's easy to construct and you can do a lot of things. So we'll spend some time with Hopf oscillators. So Hopf oscillator, as you already know, is given by these equations right at the top. X is given by this equation, Y is given by this equation. Thing is, they look a bit complicated, but if you convert it into polar coordinates, r and theta, using this and this equations, it looks very simple. It actually, you can show that it is this, so which is can be shown like this. So take these two and calculate xx dot plus yy dot. So if you do that, here xx dot will be x minus xy plus mu x square times all this. Yy dot will be it will be again plus xy plus mu y square plus all this whole thing. So if you add up these terms, get cancelled, and you get mu x square plus y square times 1 minus x square minus y square. So you get mu of r square into 1 minus r square. So you can show that on the left side, this again can be written as half of d by dt of x square and half of d by dt of y square. So again, it is half of d by dt of r square. Right, so if you cancel r on both sides and cancel 2, you get dr by dt is equal to mu r into 1 minus r square. So it's a very simple equation. And you can easily see that what this is saying is if you plot the right side, right, so this is r dot and this is r, you simply have a curve which looks like this because it has 0 at r equal to 0, the another 0 at r equal to 1. Right, and within this interval, it is positive because for r less than 1, it is positive, and after that, it's negative. So if you start from here, it will you go to you increase, you go to 1. If you start from, you go to, so we already know this, right? R tends to 1. Now similarly, if you look at the theta dynamics, so theta is given as tan inverse of y by x. If we differentiate this, theta dot is equal to 1 by 1 plus y square by x square into x y dot minus y x dot by x square. So if you take these two equations and calculate x y dot minus y x dot, right, you and simplify the whole thing, you just get theta dot is equal to, in this case you'll get just 1, but if if you have omega here, then you get theta dot is equal to omega. Okay, so in this case, since there is 1 here, you just get omega dot equal to 1. Okay, so what this means is, for this system, R tends to 1 and theta simply goes round and round at a speed of omega. So that's the limit cycle oscillator. It's a very simple kind of oscillator. Now, the advantage of Hopf oscillator is you can also write this whole thing in the complex variable domain, in the complex domain. And math looks very clean, very elegant. So for example, you can write the same equation in complex variable z, right? Z is equal to x plus iy in this form. So I omega z plus 1 by mod z square times z. If you want, you can expand this into x and y, in terms of x and y, and you will get those two equations. Okay, you can do it as an exercise, as a homework problem. Now convert this into polar coordinates, where z is equal to r into e power I theta. If you plug it in here, dz by dt will be e power I theta into r dot plus ir into e power I theta into d theta by dt. And so, and this is on the left side. On the right side also, if you plug in this, you get I omega into r into e power I theta here, and 1 minus mod z square is 1 by 1 minus r square times r into e power I theta. So this is equal to this whole thing, right? So if you expand that further, you can first of all cancel off e power I theta on both sides. Then you're left with r dot plus ir into theta dot is equal to I omega r plus 1 minus r square into r. So this is imaginary, real, imaginary, real. So separate imaginary and real. You get this and this. Okay, so again we recovered the same equation. So we can see that this complex form of the equation is same as the real form of the equation involving two separate equations. Okay, so now what we'll try to do is we want to, in the long run, right, construct, so rework the entire neural network theory. So in your deep learning theory, deep network theory, you might have, some of you might have had some experience in that. There are many different kinds of models. So you have recurrent networks, or sometimes special cases called Hopf networks, right? Or you have autoencoders, you have self-organizing maps, you have deep networks and convolution networks, and a whole lot of models which you study in neural networks. What we want to do is construct oscillatory versions of each of these models and try to show that such models will be closer to brain dynamics than the static network, deep networks, relational deep networks, which involve sigmoidal neurons and things like that, or even very detailed spiking neuron networks, which are more difficult to handle because of the spiking activity. So we feel this is a middle ground, and if you can construct such models, you can come up with very elegant brain. We can come with very elegant brain models. The advantage of such models, I think, is they are not only good models of brain function, but they also have a lot of interesting artificial applications. So they're really the middle ground. This is what we want to show. So we've already achieved this off-field network oscillatory with the same complex neurons. And autoencoder oscillatory, we have done it in one way, but we can do it in other ways also, which we have figured out more recently. This we haven't done, but we are thinking about it. We have some ideas of how to do it. This we have mostly done. There's still a few glitches we need to fix. And this is only a special case of this, so it's kind of trivial. Okay, so let us go ahead and try to construct one such a network, right? And let's try to build the basis, build the preliminary basics to achieve that. One basic thing that you need before you even go ahead and start thinking of constructing networks is, let's take a single oscillator before you even go to a network. The output of this is the complex state Z, and I give some input current I. Okay, so now this Z has the oscillator has its own frequency omega, and input has its own frequency. I'll call this omega naught. Okay, let us say the two frequencies are initially different. So input, let us say, is a slow frequency, and oscillator happens to be a high frequency. So when a low frequency thing is given as input to high frequency oscillator, right? Is it one of, if you want to train it, one of the basic things that basic features of training that you would like to see is the oscillator frequency getting tuned to the input frequency, right? So that means, can you think of a learning algorithm by which omega slowly tends towards omega naught, so that after that the oscillator frequency also is in sync with the input frequency. So it will be just like this. There may be a phase difference, that's okay, but you want it to constantly get tuned to the input frequency. It's just like radio gets tuned to the radio frequency, this radio station broadcasting frequency. So similarly, can you tune the oscillator frequency so that it constantly tracks the input frequency? So even if the input frequency is slowly varying, the oscillator frequency should be able to track it. So this is what we want. So the equation for that, I won't go into derivation, but equation for that, for omega, how to change omega, is given by this. Okay, so the external input we assume is a complex sinusoid given by I naught into e power I omega naught t plus phi. And so because we don't know the frequency of the external input explicitly, we only know it as a sinusoidal input. We don't know what is the underlying frequency explicitly. So just by looking at the oscillation, the oscillator should be able to tune its frequency. So the learning rule for that is, so this is kind of, we have taken a learning rule that was derived for real oscillators and then kind of extended this to the complex case. Is minus epsilon into I naught is this, into sine of this phi is the intrinsic oscillation of the oscillator. Okay, so Z has R and phi. So this is that phi. Omega naught is the input oscillation frequency, and phi is the phase of the input. Okay, so this value. So how is it valid? So it is straightforward to present some argument. So phi, you can think of it as omega t plus some phase value. Okay. So the thing is, how is this assumption valid? Because this coupling strength by which the input influences oscillator, that is epsilon, we assume it is a small number. Okay, so therefore the external input doesn't seriously disturb the oscillation and introduce huge harmonics and things like that. Oscillator will still go at its own frequency, but there will be some phase difference. So that is what will happen if the input strength is small. So we assume that. So if you plug this into this equation, so omega naught is equal to minus epsilon sine omega t plus some zeta minus omega naught t plus some phase. Sorry, so some phase that is minus phi. So now imagine initially omega is, so this is initial value of omega. So this is much bigger than omega naught. Okay, so this will be leading. So even if these two things have some other values, zeta and this phi, after some time this will dominate the expression, this whole phase value, total phase. And omega, this whole thing will start becoming positive because omega is greater than omega naught. Then what will happen, since sine is an odd function, this will become negative, right? So omega will start decreasing because omega dot will be negative. So similarly, if omega is actually smaller than omega naught, the opposite thing happens. Okay, so you can easily intuitively argue why this kind of an expression will give you in a situation where the oscillator frequency keeps tracking the input frequency. So you can see that in this numerical example. So initially, so I forgot which is which. Blue is, I guess, the oscillator frequency, and the red is the input frequency. So now initially both are quite different, and the learning begins right from the beginning. Right. So after some time, the oscillator frequency slowly tends towards the input frequency, and after that, both merge. So it's able to track the input frequency. Now omega in this plot shows how omega adapts. But omega is initially 40, and since oscillator frequency initially 40, external input frequency initially 30. Right? Because of training, it tends towards 30 and stays there. But one interesting thing you will find in the manner in which the oscillator frequency has tended towards external input frequency is look at this shape. I mean, it's like a steep fall. It's like a falling stone, right? Stone falling to the ground. So it just makes a straight fall and right and head on, and then after that remains flat. So usually in a lot of these learning algorithms, when a quantity approaches a kind of a target value, the approach is very often exponential and asymptotic approach, right? But in this case, it's not an asymptotic approach. It reaches the target value in a finite time. After that, it stays there. So, which is very interesting about the way the frequencies learn. Okay, so that is the first step. So we have shown how you can have a single oscillator and you can present a sinusoidal input to the oscillator, and we can train the oscillator in such a way that the oscillator frequency tends towards the input frequency. That's the first step in training. Now let us take two oscillators, all right, and see how you can train it to do something. So if you want to take just two oscillators, how do you couple them? So we'll think of one kind of coupling. You can have many kinds of coupling. You can have like a unidirectional coupling where one oscillator sends input to the other oscillator and there's no feedback. Or you can have feedback, but you can make the feed forward and feedback weights, the coupling strengths are different so that the coupling is asymmetric. But we'll take a special kind of a coupling where the coupling is symmetric, right? By symmetric, I'll say it is symmetric in a special sense. So let us look at that. So this is the dynamics of the first oscillator. This is the dynamics of the second oscillator. The Z1 is the variable first oscillator. Omega 1 is the frequency of the first oscillator. Similarly, Z2 and omega 2 are for the second oscillator. Now for coupling, you take Z1, take Z2 and pass it through take the real part of that and pass it through a weight and add it as an additive term to the first oscillator. And similarly, take Z1 and add it in the second equation. So we are looking at basically what happens when there is real coupling. Okay, what we are trying to say is, although we have two oscillators, both have complex numbers. So you have x1, y1 here, and x2, y2 here. So coupling coupling means you can have real coupling means coupling only x1 with x2. The other two that don't directly participate in the coupling between the two oscillators. They indirectly participate because x1 influences y1, y1 influences x1, x2 influences y2, y2 influences x2. Okay, in that sense, everything influences everything. But in the equations, the direct coupling is only between the real parts. This is what we mean by real coupling. And there's a coefficient for that. I'll call this W12. Now, since it is a complex variable and you have two components, x1, y1, x2, y2, you can think of a more general kind of coupling where x1 is coupled to x2, y1 is coupled to y2, x1 is coupled to y2, x2 is coupled to y1. All four possibilities can be used. Right, we'll see what happens with that kind of coupling. So this is real coupling, and we'll call this complex coupling. So let us see what's the difference between these two. So first, let us look at real coupling. So in this case, we'll look at a special case where omega 1 is equal to omega 2. Okay, so in this numerical example, omega 1 is equal to omega 2 is equal to 5. And the coupling strength is that W21 is equal to W12 is equal to 0.5. So it is symmetric coupling. Okay, so real coupling, and not only that, it is symmetric. Right, so see what happens when the coupling is symmetric and if it is a positive value, 0.5, the two oscillators are in phase, so phase difference goes to 0. Initially, there could be a transient if there's a phase difference, but it will quickly go to 0. Something, okay, that's fine. And if coupling is negative, initially there is some other phase, but after some time it will go to a totally out of sync, out of phase situation, and the phase difference goes to pi. Okay, and you can also see that no matter what your coupling strength is, assuming only make sure it's not very big, right? So that it will distort the oscillation, and you can even have complete cessation of oscillations if the coupling strength is very big, because it's no more a Hopf oscillator. As long as it is small and positive, you will see that they come to a phase difference of pi if the coupling strength is negative, and phase difference of 0 if the coupling strength is positive. Now, point is that's not very interesting, because when two oscillators are coupled, they can in principle oscillate at any phase difference, right? But if you say, no matter what I do, I can only achieve 0 phase difference or pi phase difference, that's very restrictive. So can we extend this model in such a way that I can have arbitrary phase difference? Okay, the answer is it's possible. So for that, you have to use complex coupling, right? So just like what I said here. And so the complex coupling can be expressed in kind of polar form like this. The amplitude A times e power minus I phi, and amplitude e power I phi. So the thing is, both the coupling strength, these are the coupling strengths, they are complex, but you see that they are complex conjugates. Okay, one has here plus sign, other has minus sign, and that's important. You need to have that. So if you have that kind of coupling, then let us see the equations change like this. First equation is this plus the coupling strength, right? A into e power I phi times Z2. Here it is A into e power minus I phi times Z1. Okay, so that's how we couple them. If you couple them, what happens? So let us look at that. So now we know how to convert the complex number into polar coordinates. So Z1 becomes R1 and theta 1, Z2 becomes R2 and theta 2. And if we have done the exercise before for a single oscillator, so you apply the same tricks and convert this into polar form. What you will get is R1 dot is equal to mu minus R1 square into R1. This is like a single, single oscillator without any external, without any coupling. And because of the coupling, you have an additional term, which is this. So A R2 into cos of theta 2 minus theta 1 plus phi. So phi is the angle of the coupling. Okay, so this value shows up here. And theta 1 dot is given by omega 1. If you had only one oscillator, you will have just this will be the equation, theta 1 dot equal to omega 1. But because of the coupling coming from the other oscillator, you will have this additional term, which is A R2 by R1 into sine of theta 2 minus theta 1 plus phi. Okay, so by symmetry for the other oscillator, it will be again R2 is equal to blah blah blah, and theta 2 dot is equal to, so omega 1 you have omega 2 A R1 by R2 sine theta 1 minus theta 2 minus phi. Okay, because coupling angle is different in different directions. So now what we'll do, what are we looking for? We are seeing if you can achieve arbitrary phase difference. So that means, can theta 1 minus theta 2, right, can it be arbitrary? Any desired value, is it possible? So let us look at that. Let us call the phase difference psi. Okay, theta 1 minus theta 2 is equal to psi dot is equal to theta 1 theta dot minus theta 2 dot is equal to omega 1 minus omega 2 minus of the sine. So this is theta 1 minus theta 2 is defined as psi, right? So here, so psi is equal to theta 1 minus theta 2. If you plug it in, you have minus of sine psi minus phi by R1 R2 times R1 square plus R2 square. Now R1 and R2 don't give much problem, because if the coupling strength A magnitude is small here, right, then R1 simply will go to root of mu, R2 will go to also root of mu. So that's not a big problem. So you can think of this whole thing as almost a positive constant, right? So let us look at this term. So you have so now one other thing is omega 1 is equal to omega 2. So therefore this part is 0. Right, so you are left with this. So at steady state, omega psi dot is equal to 0. That means this A. So I'll put let R1 is equal to R2 is equal to root mu. So if you do that, you get cancelled off and you get mu just 2 here. So that's why it is 2A times sine psi minus phi is equal to 0, right? What does it mean? If so, psi equal to phi will be a steady state, right? Will be a stationary point. So therefore, theta 1 minus theta 2 can be made equal to phi, and phi you can choose whatever you want, right? You can make it equal to, I don't know, 37.4, say 42 degrees, something like that. Right? It will still work, and your phase difference will stay there, right? You can make it whatever you want. And how do you know this is stable? Because you can easily see that if psi is more than the required, right? If you more than required value of phi, right? Then this will become negative, and it will psi will be pulled down. And if it's less, it will become positive, so it will be pulled up. So it is stable. It's stable state. You can look at second derivative also and verify that. So let us look at that with a numerical example. So coupling strength amplitude is small, 0.2, and the phi is pi by 4. Okay, and the frequencies are both the same. Omegas are equal to 5. Then what happens? So the phase initially some random value, but after some time, right, it settles at pi by 4. So this is pi by 4. Okay, so which is what you want. You can show that. Now this result is already there. We didn't come up with this. But I'll show you one extension we have done, which can give you a much more general result than this. So we have seen that if you take two oscillators with same frequency, life is simple, and you can achieve like arbitrary phase difference. Because you want a network which is general. You cannot have a network in which oscillators can have only certain specific values of phase difference and things like that. Okay, so you can achieve that generality if the frequencies are the same. But if you want to construct a general network of the brain, then you can't have all the oscillators oscillating at the same frequency, right? Because in the brain, you have all these, theta, alpha, beta, gamma, and so on, right? Which and delta at lowest. So there are all different frequencies. So obviously, brain has to have many oscillator frequencies. But the problem is this is where you have a really deep, challenge. If you couple two oscillators with very different frequencies, the dynamics gets very complicated. I mean, none of the simplicity that we have seen until this point, will carry over if the frequencies are quite different. What will happen is if the frequencies are very similar, like omega 1 is, let's say, omega 1 is equal to omega 2 plus a small number epsilon. So epsilon is less than 1. Okay, so if for that special case, what will happen is the theta 1, which is the phase of oscillator 1, will be greater than theta 2, and omega 1 will tend towards omega, and omega 2 also will tend towards omega, and omega 1 will be greater than omega will be greater than omega 2. So if this is omega 2, this omega 1 is greater than omega 2, and assuming they are very close to each other and coupling strength is also sufficiently high, so that situation is somewhat intractable. Okay, so here I assume the opposite thing. So then what will happen? The two oscillators will come to some kind of a compromise. They attain some kind of intermediate frequency. It doesn't have to be a perfect average, some intermediate frequency. And at that point, the phase of the faster oscillator will be higher than the phase of the slower oscillator, or the faster oscillator will lead the slower oscillator, right? Because they'll come to a common frequency, omega. So all this is possible if the oscillator frequencies are quite close to each other, sufficiently close to each other. The thing is that is good, but that is still quite restrictive, because if you look at brain frequencies, they're not all close to each other. You can have anywhere from 0.1 hertz to 100 hertz. So that's not close. That is 3 orders of magnitude. So obviously you cannot have a theory where you assume that all oscillator frequencies are very close to each other. And a lot of models of synchronization assume that, and they assume that all the frequencies come from a nice Gaussian distribution and with a small standard deviation and stuff like that. But all that is okay if you want to develop some special mathematics. But if you want to develop a brain model, all that is not okay. Right, and let us see this result using this simple numerical simulation. So in this case, we are starting with one oscillator. Omega 2 is 2.2, omega 1 is 2. So the frequencies are different but quite close to each other. Now we vary the coupling strength. Coupling strength is epsilon, right? And we are doing real coupling. So what happens is epsilon 0, oscillator 1 will be at 2.2 hertz, oscillator will be at 2 hertz because that's a native frequency and they're not coupled. But as you increase epsilon, the two frequencies vary, right? The oscillators don't oscillate anymore at their native frequencies, but they are now influenced by the other oscillator and moving towards other oscillator. So that happens, but as you approach, as you increase epsilon further, right? I don't know. It's like when two people coming to a compromise. Just before they come to a compromise, they pick up even stronger fight. It's something like that. So they actually briefly deviate, diverge further, and move away from each other, and then after that they kind of come to a compromise. And at around this value of 0.2 epsilon, they come to a common frequency of 2.1, which happens to be average, but doesn't have to be that, right? So this is possible, but then that defeats the whole purpose because we want to create a network in which the frequencies are maintained different. We don't want them to come to a common frequency, right? The frequency should be maintained different, and the phase difference should be maintained at an arbitrary value. This is my most general network. This is what I want. So here, what is happening is I'm defeating that purpose. Okay, so how do you create a network, or let's say start with just two oscillators, right? In such a way that when the two oscillators are coupled, so this is at omega 1, this is at omega 2. I want them to beat at their native frequencies, but I want the phase difference to be equal to some desired value, which is arbitrary. Okay, how is it possible? So this is the question. But so what happens? So if it is the oscillator frequencies are close to each other, you have something like this. But if this is a question. The oscillator frequencies are very different, arbitrary values, omega 1, omega 2. Actually, things get very complicated if you have the normal kind of a coupling with the real coupling. Let's see what it is. Okay, so you have lots of bifurcations, a very complicated bifurcation map, which is defined by, which is called Arnold tongues. Okay, which looks like this. So let's try to make sense of this map. So on the x-axis, you have the omega 1 to omega 2 ratio because their frequencies are different. So now let us talk in terms of their ratio. Now y-axis is the coupling strength. Now as you vary the ratio and vary the coupling strength, you will have all sorts of dynamical scenarios. So take this simple case. The two frequencies are the same and coupling strength is 0. Okay, so obviously both will fire at the same frequency because the coupling strength is 0 and anyway frequencies are the same. So that is trivial. Now I go straight up, okay, at the same value. Omega 1 is equal to omega 2, and I keep on increasing the coupling strength. What will happen? We have seen before already that it will just show. It will just have a kind of a constant phase difference, and they'll continue to fire at the same frequency. But what if I change the go off in different directions? Like if I go to a ratio which is less than 1, okay, which means omega 1 is less than omega 2, then what will happen is if I start at this like here, right, with or here a very small coupling strength, but omega 1 is less than omega 2, then what will happen is they don't fire anymore at a common frequency because this yellow zone is all the points where the two oscillators beat at a common frequency. Once you're outside it, that's not true anymore. So if the ratio is not equal to 1, if the coupling strength is too small, they don't come to a common frequency. They don't make this compromise. So for them to make this compromise, right, you need to have sufficiently high coupling strength. And the greater the deviation of the ratio from 1, the greater deviation from this vertical line, right, the stronger must be the coupling strength for them to make that compromise. So that's why as you deviate more and more from this, middle value of 1, right, you have to go to higher and higher coupling strength values to achieve that 1:1 synchronization, to achieve to force the two oscillators to come to the common frequency. So situation is so complicated even for this thing. So, but if you look at some other ratio, suppose my W1 by W2 has these two ratio, right? At zero coupling, then that they'll beat at that frequency. But if you want to deviate from that, right? So you want to go to further higher values and still have the same ratio of of coupling, then I'll have to have a sufficiently strong coupling strength. Okay, so you can see in all these cases, if I want to achieve some kind of a integral ratio coupling, which is called entrainment, by the way. So when it is frequencies are the same, we call it synchronization, and the frequencies have an integral ratio, it's called entrainment. All right. So if you want to have that entrainment, even when you are deviating from that integral ratio, then you need to have sufficiently strong coupling strength. So as you go higher, this thing becomes wider and wider, right? Or if you want it to be wide, you have to go higher. That's what it means. Therefore, you have this kind of a triangular regions. These are called the tongues. They are the Arnold. It was worked out by V.I. Arnold, I guess, the Russian mathematician. So you have so many of these tongues, and if you go to these tongues that are large and in the forefront correspond to simple integral ratios. Okay, where p by q, where p and q are small numbers, small integers. But if you go to these smaller tongues, which are more in the background, they correspond to much more complicated integral ratios. Like for example, 27 by 31 or something like that. It's possible. So if you want much bigger integral ratios, then you have to go to even deeper tongues and even thinner tongues and so on and so forth. So it's a bloody nightmare. It's a very complicated situation. So the point is, even if you couple just two oscillators, right, where the frequencies are different, it is so complicated. And one more thing I forgot mentioning. What is the meaning of, so within that, inside these tongues, the oscillators will fire at an integral ratio. Okay, but what's the meaning of the regions outside the tongue? So suppose something like this, or here, or here. Okay, here there is no such integral ratio between the frequencies. Right, so there's no relationship between two oscillations. They're just doing their thing. They're just oscillating at whatever frequency. So if you are here, your ratio is omega 1 by omega 2 at this point. It is some vague value, and they'll be oscillating at that frequency. Right. So outside these tongues, I mean, there is chaos. It is. I'm saying in a general sense, not the mathematical chaos. Outside it is very general. Okay, only inside this there is some semblance of order where the oscillators kind of come to a compromise and agree to fire at some integral ratio. Okay, so you can see the situation is very complicated. Now, can you make it more regular? Can you control this whole thing? So this is where we have made a special proposal, and this is not there in literature. Actually, we couldn't find this in the literature, and it was surprised that this simple idea, how come people didn't think of it before? Right. So here, what we are trying to do is, see, obviously, when two frequencies are different, uh, you cannot have, first of all, how can you even talk about phase difference? Because when two frequencies are the same, you can talk about phase difference. And then you can ask, can I make that phase difference equal to some desired constant value? Okay. But if the frequencies are not even the same, how can you talk about phase difference? How can we talk about a specific relationship between the two phases? Okay, so that is possible if you look at this extended concept of phase difference, which we call normalized phase difference. What is normalized phase difference? Again, you call it psi, which is theta 1 by omega 1 minus theta 2 by omega. Okay, so that means one of the oscillators is going at a high frequency, other is going at a low frequency, right? That is okay, we don't mind that. It is just that you take this theta 1, the phase of this one, and normalize it by dividing by omega 1. So you get a kind of a normalized phase, take theta 2 and divide by its own frequency, right? Now, the difference between this normalized phase and this normalized phase, which we call normalized phase difference, that I want to be equal to my desired value. If that is true, then I'm satisfied. I don't mind. Can we achieve that? Okay, for that, we developed a mathematical trick called power coupling. Okay, let me intuitively explain what power coupling is. I'll work out the math in the next class. The basic idea is, yeah.
Just a small doubt, so that the things will not go over the head. So that the Arnold tongue figure that you showed, no, in that a couple of slides back.
Yeah.
So where the coupling strength versus this one.
Yeah.
So we can see that at 1 and when omega 1 by omega 2 is equal to 1 or 3 by 2 or 2 by 1 2. So the synchrony is much higher as the coupling strength increases. But when it is 1.75 or any other value in intermediate, so we don't have that much synchronization. So is it required that we have to select that omega 1 and omega 2 values? If we have any other omegas, then we cannot achieve that perfect synchronization or something like that?
Yeah. So good question. Let me explain that. So basically what is happening in this graph is, so let's take a point here, okay?
Okay.
Let's take a point here. So here the value is, the ratio is 2 by 1. Let us say omega 1 is 2 and omega 2 is 1, okay? So this is something less than that. So let us say omega 1 is 1.9. Sorry. Yeah, 1.9. Omega. So at this point, let's say omega 1 is 1.9 and omega 2 is 1, right? So they are not in any simple integral ratio. It is, you can even make it more complicated, omega 1.912 blah 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 something. So at this point, so what this point says in this point in this map, what it means is, this is inside this tongue, which means the oscillators are actually firing in a ratio of 2:1, right?
Okay.
But the intrinsic oscillator values, omega 1, omega 2 values are not in 2:1 ratio. They are in some other value, because if you take the x-axis of this, it is that, right? So it is less than 2. But because of the coupling, they'll come to some kind of a compromise. It's not a perfect compromise. They haven't come to a common frequency. They are saying, okay, look, you are at 2, I'm at, you're at 1.912, I'm at 1. So let us come to a common frequency, and what might happen is, this one fellow will actually go down a little bit, this also will go down a little bit. They might operate at 0.9 and 1.8 or something like that.
Okay.
So they are not operating at their original frequencies.
Okay. They will basically try to come into that ratio, that match that
ratio.
Right. Okay.
Yeah, they'll deviate from their original omega 1, omega 2 values and come to some kind of a nearest integral ratio.
Okay. Yeah.
And that they will do only when the corresponding epsilon is sufficiently high. Suppose you are here.
Okay.
Exact same oscillators and same frequencies, but it's outside the tongue. What does it mean? They are not coming to any 2:1 ratio.
Yes.
They'll be doing their thing. So this is 1.1, 1.912, let us say, right? And 1 is to 1. They'll keep on oscillating like that. There is no agreement. There's no compromise.
Okay.
To want the compromise, you have to increase the coupling thing sufficiently. Then even that is a weak compromise. It's not. They're not coming to 1:1.
That's right. So is there any the coupling strength between these two oscillators? So is there from the graph, what we can see is that higher the coupling strength, better is the synchronization. So should we always select that higher coupling strength, or is it there is some compromise also on that coupling strength?
Yeah, good question. Because yes, if you higher the coupling strength, higher synchronization. But the problem is, in fact, if I start from here and keep on going to at a very high value, I enter this 1:1 region.
Correct.
Okay,
Yes.
which means two oscillators. So it could be 3.2. So let's say 1.4 is the ratio here. Okay.
Yes.
But if I take epsilon sufficiently high, then they'll be kind of forced to beat at same frequency, 1:1.
Yes.
So something as different, as big as 1.4 is forced to 1:1, right? And then they'll keep firing like that. So they achieve synchronization. But what is the point? We don't want that.
True.
Right?
Yes,
Because in
yes.
the brain you have many frequencies. We don't want all oscillators to come to a common frequency.
That's right. Yeah.
So thing is, we would ultimately like the oscillators doing their own thing, but
Okay. Mm.
right, but we want that to be there to be some kind of a stable phase difference among between them.
Okay.
Here,
Yeah.
what is happening? If you increase the coupling strength, they'll come to some kind of a common frequency or an integral ratio. Okay.
Yeah,
If
right.
you
Yes.
don't increase the coupling strength, they're completely haywire. They do their own thing. There's no control on the phase difference.
Correct. Yes.
It is like this, in parenting, right? If you yell at the kids and you beat them up and yell at them, take them to task and all that, they'll become totally quiet and submissive and they don't do anything, right?
Yes.
If
Mm.
you completely let them loose, do whatever they want, again they're completely out of control. They don't do their homework and things like that. I'm just giving some crude analogy. It is something. It's two extremes, but we don't. Both the scenarios are not good for us if you want to develop a generalized brain model.
Right. Yes.
Right. So what we said is, what we want is, we don't want the oscillators to come to some common frequency of with integral ratio and all that. The frequency of first one is omega 1, other is omega 2, and the phase of the first is theta 1, theta 2. Then we want the normalized phase difference, that is normalized phase of the first one, normalized phase of second one, should have a stable difference, a constant difference, or should tend towards a constant difference, no matter what omega 1 and omega 2 is. Is that possible? Right? In the normal theory of coupled oscillators, this was never there. But we felt that that's what you need if you want to come up with a generalized brain model. And interestingly, you can achieve this using a very simple trick, and the trick is possible only in the complex variable domain, which is what we call power coupling. I'll just intuitively explain what the idea is, then I'll work out the math in the next class. So basically what we want is, if I have an oscillator like this, and this is the input, it is receiving input from two other oscillators. Let us say this oscillator has high frequency, this oscillator has low frequency, this oscillator has medium frequency. When this oscillator sends its signal to this oscillator, at the connection, at the synapse, this frequency must be transformed into something else, right? And the transformed frequency must be same as the frequency of this oscillator, right? So when this oscillator, this fellow is listening to this fellow, he only hears his native frequency. Okay, so he has no problem. So similarly, when this fellow listens to this fellow, this has a very low frequency, right? And this low frequency is transformed into this middle frequency at this connection, and this fellow only listens to this. So many different people are talking to this fellow at different frequencies, but all those frequencies are transformed into the frequency of this fellow at the respective connections, and this fellow listens to, he gets to hear only its own frequency. So there's no problem. Right? It's like to give another silly analogy from human world. Right? Let us say a man and woman are talking. Okay, so man and woman. The frequency is low frequency for a man, well, speech frequencies. Frequency has shrill and high frequency for a woman. Imagine they're talking through some kind of a mouthpiece or some kind of a device. So where when the man speaks to the device, it shifts the frequencies to high frequencies, and woman will hear it like a female voice. Okay, and when the woman speaks into the device, imagine some kind of a special telephone network, right? It will shift the frequencies to low frequencies, and a man will hear it like a man's voice, right? Then there no more no more fights in the world. Okay, so we want to achieve something like that. How do you achieve that? You can do it very simply using in the complex variable domain, because if z1 is the first variable with this kind of a expression, its frequency is omega 1. How do you convert it into omega 2? Just raise this to the power omega 2 by omega 1. If you do that, right, very simple algebra, omega 1 omega gets cancelled, you get omega 2. Okay, so by simply raising this to a certain power, you can convert z1, which is oscillating at omega 1, to z2, which is to another variable, which is oscillating at omega 2. Okay, that's the magic lamp that we want to introduce. So let us look at it has very nice mathematical properties. Let us look at the consequence of this and how you can construct networks with this, right? All that in the next class. Okay. So any questions? Might be slightly overhead, but I want to go slow. That's why. And if you have questions, please ask. Okay, no questions. Then okay, let's continue on Friday's class. Okay.
Right. Yeah, thank you, sir. Yeah, one more thing, sir. Actually, like initially, one in an oscillator, you applied a current, no? Like low frequency signal you applied to that particular oscillatory region that was oscillating in a higher frequency. So now the oscillator frequency is trying to reach towards the low frequency, from the high frequency towards the low frequency, and there was a waterfall kind of curve where it is achieving that particular movement to one frequency to the other frequency in a finite time.
Right. Yeah. So no, the thing is, wait. So the first example theory I showed is where oscillator frequency tunes itself to follow the input.
Correct. Yes.
The omega variable parameter is changing, so that the oscillator can follow the input frequency. But in power coupling, the signal coming from one oscillator is transformed at the synapse, at the connection, and that is what is presented to the other oscillator. The omega itself is not changing.
Okay. Yeah.
Which is a very important difference.
Okay.
So thing is, every oscillator will continue to be what it is. We are not asking them to make any compromise.
Right.
But when they talk to, it's like two people talking in different languages. Instead of asking both of them to learn the other person's language, or instead of asking both of them to learn a common language, we are saying you speak whatever you want. We have a device which will translate your language into other person's language, so everybody can communicate happily without any compromise. Right. So that's what we're trying to achieve using the special power coupling process.
Okay.